So I work for Intel on the Lustre network LNet layer. This is the module that's responsible for the networking for the Lustre file system. Over the past year, we've been working on the MultiRail feature with SGI. So I'm going to do a quick recap because LNet Health, or I call it LNET Resiliency, depends on that. So I'll talk a little bit about MultiRail. Then I'll share some performance numbers we got on the SGI system. Then after that, I'm going to jump on LNET Resiliency. So speaking quickly for MultiRail, prior to MultiRail, you could configure only one network interface per LNet network. And if you had a system with multiple network interfaces, you had to configure each network interface on a separate LNet network. That obviously resulted in a very complex configuration. So if you had something like this where you had a big machine with multiple interfaces, you couldn't really put everything on the same O2IB network. You had to put each interface on a different network, and then you had to fake those connections on the other nodes that only had a single interface. So we needed a way to make this configuration simpler. So we had a few objectives when we started working with SGI. They have really large machines like the SGI UV300 with 32 sockets, and it's a NUMA system, or the 3000 with 256 sockets. So these large systems with many terabytes of memory, they require a lot of bandwidth. So we wanted to increase we wanted a way to increase the bandwidth without really making the configuration a lot more complex. Also, those NUMA systems benefit when the memory buffers used for RDMAing the data are close in the system's topology to the interfaces. Another driver was we wanted to be able to be hardware agnostic, so we didn't want to implement MultiRail for OmniPath and Mellanox and Ethernet. We just wanted to do it at the LNet level so that all the underlying hardware benefits from it, and obviously simplifying the configuration. So we wanted to end up with a configuration like this. Just one network and have multiple interfaces connected to that network. So implementing it at the LNet layer gave us a few advantages. First, we were able to connect multiple interfaces to one network. We were able to connect, obviously, multiple interfaces to different networks, and we're able to use all those networks, all those interfaces simultaneously. We don't have to stick to only one interface or one network. If, for example, a peer lives on multiple networks and we can reach it on multiple networks, we can select the interface depending on a few criteria, including the NUMA criteria, the buffer that we're trying to RDMA, how close is it to the network interface, and how busy the network interface is. And the last criteria is if everything is equal, we'll do a round robin. And because it's at the LNet level implementation, for example, OmniPath and Mellanox are not compatible over the wire, so we can configure OmniPath on one network, Mellanox on another network, and then LNet would be able to use those networks simultaneously, even if they're talking to different machines or to different nodes or to nodes that exist on both networks. So there are two basic configurations when you're trying to configure MultiRail. First, you have to configure the network interfaces, the local network interfaces themselves. Say, for example, you have an O2IB0 and you configure IB0, IB1, and IB2 on it. And then the second configuration step is you want to say, okay, well, for each node, you want to configure the peers that this node talk to and all the interfaces that these peers have, so that they know to use those interfaces. So, for example, say you have two interfaces, each one with you have two nodes, each one with three interfaces. For peer A, you want to configure peer B's interfaces on the right. And for peer B, you want to configure peer A's interfaces. And Once that's done, each node knows the other peers' interfaces, and then it can talk to them, and it can utilize all of them. But obviously, if you have a really large cluster with thousands of nodes, configuring everything manually becomes a really error-prone process. So we wanted a way to be able to reduce this configuration burden. What we did is we implemented something called dynamic discovery, and this adds the ability for LNet to be able to discover the peers that it's talking to on the first time it tries to talk to it. So, for example, if the upper layer portal RPC, in the case of Lustre, tries to send a message to peer B, what we do at the LNet layer is first we ping that peer, and we get its interfaces back and a feature bit mask. And if the MultiRail bit is set in the feature bit mask, what we do is we know now that it is MultiRail capable, and then we push our interfaces to it. And through this simple protocol, we're able to, both sides of the local and the remote now have the peer information, the interface information, they're able to use it. So this, now we don't then the configuration steps that I mentioned earlier is reduced to only configuring the local interfaces. So in summary, MultiRail increases the bandwidth quite a bit, and it's good for servers because you don't have to buy new or faster interfaces. If you're able to expand it and add more interfaces to the server, then it will automatically scale the bandwidth. And it's useful for large clients like the UV, as I mentioned before. So, whoa. Okay, this is not the updated. I'm missing here the performance numbers. Anyway, I'll try to remember them off the top of my head. So SGI, maybe is it here? No. Okay. Sorry, got caught off guard here. SGI, what we did with the SGI UV system is for SC16, they built a system with 32 sockets and 16 terabytes of memory and 8 OmniPath interfaces, 8 OSSs, and for each OSS, they had 4 OSTs. The theoretical maximum was something around 34 gigabytes per second for 34 gigabytes per second for sequential reads, and 70-something gigabytes per second for sequential writes is 36, and sequential read is 70s. With MultiRail, we're able to get to sequential write to be about 31 gigabytes per second, and for the sequential read, we were able to get about 68 gigabytes per second. So it was clear that MultiRail did achieve its purpose of increasing the bandwidth. So with that, we wanted to be able to also increase the resiliency of the node. So now that we have multiple interfaces, why can't we use all the interfaces to do error recovery? Right now, Lustre error handling is kind of expensive. If there is like a failure, depending on which RPC is lost, we can evict the entire client. But if that client is reachable via different interfaces, so why can't we try the different interfaces before we declare that message failed? So that's when LNET Resiliency comes in play. I'm going to cover quickly what messages LNET uses. So there are 4 main messages. There's the put, the ACK, which is an optional response for the put, the get, and the reply, which is the response for the get. That gives us 3 different combinations to work with: a bare put, a put plus an ACK, or a get plus a reply. An RPC, like formed by the portal RPC layer, can be a combination, one or more of those combinations. So our goal with LNET Resiliency is to be able to use all the interfaces on the remote and the local nodes before we declare a message dead. But obviously, we can't continue resending forever, so we have to have an upper limit, time limit, before we declare that message failed. And again, we wanted to implement it at the LNet layer so that we're able to fail over to different types of interfaces. So just covering quickly what an LNet network looks like. You can have directly connected nodes, or you can have nodes separated by multiple routers. What LNET Resiliency is concerned with is ensuring that a message gets to the immediate next hop without failing. Or if it fails, we're able to report that back up to the upper layer. So I'll cover quickly those three combinations I talked about. So first, the put message, which indicates that we're about to RDMA some data to the peer. This is the simplest LNet message, and there is no response to it. So LNet can't really do much about it. If we send a put and it gets lost, or like the client or the peer drops it, there's nothing we can do about it. So whoever requests that put, or the upper layer that requests that message, has to make its own recovery mechanism for it. For the put plus ACK, because we are expecting an ACK back, we are able to currently implement a timeout. And if we never receive the ACK, we're able to push a timeout event up to the upper layer. The ACK message is sent at the LNet layer, so we don't really wait for the put to be processed by the upper layer. Once LNet receives the put, it sends the ACK response and then propagates the put up to be processed. So at the sending side, we're able to say, well, if we don't receive the ACK, then we can time out within a reasonable amount of time. Get semantics means that the sender node is requesting some data from the peer, and the same applies with get the reply. We don't really wait for the get to be processed. We just send it right away. And if we never receive it on the sender side, then we fail. We can time out. So quickly, LNET Resiliency then is concerned with ensuring that a message is delivered to the next hop. And for the put plus ACK and the get plus reply cases, we're able to do LNET timeouts. Or LNET can maintain its own timeouts. But what about the failures that LNET has to handle? So there are three main failures that we need to be able to handle at the LNET layer. First, the local interface, if it fails, we need to be able to handle that. If the remote interface fails, which means it can't send or receive, we need to be able to handle that. And if there is somewhere some problem on the network, we need to be able to handle that. So I'll break down those three cases quickly. For local interface failures, the LND reports some failure. So I'm not sure how familiar you guys are with it. The LNet, there's two layers to it. There's the LNet layer and then the LND layer. The LND layer is the network driver. And this is concerned with talking, for example, we have one auto IB, which is talking verbs to both Omnipath and Mellanox. And we have the SOC LND, which talks to the Ethernet. So at the LND layer, we're able to propagate failures. For example, there are specific messages if the adapter gets unplugged or there's a catastrophic failure with it, those messages those events get propagated to the LND, then they get propagated up to LNET, and LNET can then just not use that interface anymore for traffic. And if there are other interfaces available and we can reach the peer through those other interfaces, we can start retransmitting this message on the other interface. We'll keep attempting to resend the message until either there is no more interfaces to try, or we time out. There's a configurable timeout that can be configured for how long we should retransmit for. If that times out, then we fail. For the remote interface, there's a few error cases that we want to handle. For example, if the address is wrong, or there's no route to host, or the connection cannot be established, or some parameters are incompatible, we need to be able to not fail right away, but try to a different remote interface if one is available for that peer. So in this case, the local interface is working, but we're not able to establish a connection with it. We call this soft failure because sometimes you can have an issue with connection that gets fixed later on. So the key point was soft failures versus the hard failures that I talked about earlier. Is soft failures, we will retry the interfaces, and we'll go round robin or whatever over the interfaces and if we reach the end, we'll retry again over the interfaces that we could have tried before until the timeout expires. So in this case, the local interfaces I said that already. LND reports these errors to the LNet layer, and then LNet attempts to resend the message over a different remote interface. If there is none available, then we fail. Then there is a path failure. This really is determined at the LND level. So there is when LNet says send a put or send a get, this actually gets translated to multiple messages at the LND level. There's a protocol between the LNDs to make sure that the put is completed or the get is completed. For each LND message, we have a transmit timeout to make sure that the LND message got received and acknowledged by the other LND. So on each LND message that gets sent, a transmit timeout is started. And then depending on when that timeout expires, we're able to tell where the failure is. So I'll break it down a little bit. So there are 3 different types of cases. So the message is on the sender's queue. And after when we're trying to transmit a message, we put it on a sender queue, and then it gets picked off that queue and posted on the wire. So the transmit timeout can expire while the message is still on the queue, which can indicate that there's something wrong locally and we're unable to process the messages fast enough. So we will have to deal with that. The message could be posted, but the transmit never completes. This indicates that we don't know exactly where the problem is. Did the far end never receive it? Did it get dropped somewhere in the network? So we'll have to handle that as well. And then finally, the message is posted, the transmit is completed, but the remote never acknowledges the message back via our protocol. So at this point, we know that there is something wrong on the remote side. So in the case of the local or the remote interface issues, the cases with the local remote, then we deal with it, as I mentioned before. We either pick a different remote interface or a different local interface. And if for the case of the path failure, where we don't know exactly where the problem is, then we'll just pick an entirely new pair of interfaces. Either like a new local interface and a new remote interface. And we'll keep doing that until the path timeout, the peer timeout expires. So with interface health tracking, we want to be able to be smart when we're picking our interfaces that we're going to send over. So we're going to maintain a health value per interface. And whenever we have a soft error on one of those interfaces, we'll decrement that value. That value will recover over time. So the net effect here is that consistently unhealthy interfaces will be preferred less and less over time. So this is our mechanism to be able to select the local and the remote interface when we're initially sending a message. Finally, the reporting side of things, we have currently a utility called LNET Control, which is used to configure LNET with its different parameters dynamically. So we want to be able to enhance this utility to extract the resiliency information and display it for the user, which can be useful for debugging the cluster, for example, or it can be displayed on some GUI, for example, the Intel Manager for Lustre, the IML, which is a GUI for configuring Lustre. So in summary, we see that MultiRail increases the node's bandwidth, and then LNET Resiliency comes in to build on top of the MultiRail infrastructure to allow resending LNET messages. And for both of those, we implemented the LNET level so that we can be hardware agnostic. And that's it. So any questions?
Yeah, I just want to understand what you were talking about, the layers. So there's an LND layer and an LNET layer. Mm-hmm. Then there's also the client server probably layer on top of that. Because I'm trying to understand because you were saying that the message goes up, you send the ACK, and then you send the message up the stack. So if it fails up the stack, then the client server comes into play to say, hey, I didn't get what I was looking for?
So there are multiple layers on top of LNet. So there's the LND, LNet, and then there's Portal RPC, and that's the layer that forms the RPCs, and then you have the client and server layers that actually maintain the file system. So LNet is really responsible for making sure that the messages get across. And if there's a failure, we just send an event up, and then they have their own mechanism. There's a retry mechanism, actually, and they evict the clients or whatever they do up there.
So you mentioned NUMA. How does that come into play here in your configuration or buffer management?
So for the UV systems, the UV actually is it's a large client with multiple racks. So if you select, and it's a NUMA system, so if you select an interface that is far from where the buffer associated with it, actually sending it over the interface, there's quite a big penalty for that. So when we're selecting the local interface, we look at the NUMA node that the interface is nearest to, and we look at where the buffer is nearest to as well. And then we we look at the buffer's NUMA node, and then we select the interface that's closest to that NUMA node, and we send over that to try avoid the penalty for the NUMA penalty. And it's actually very significant. We've seen through testing that if we select farther interfaces, the performance degrades quite a bit.
So then you're relying on the buffers to be evenly distributed across the nodes then for
Yes,
when you're,
yeah.
this is when you're pushing out. And so I mean, to have the same issues on, small, two-socket nodes, right there, NUMA.
Yeah.
The quick path issues when you're, managing incoming and outgoing traffic.
Yeah.
And so, you'll use the same mechanism then within, say, a router that's on a two-socket node?
Yes.
Would you enable that?
If we enable MultiRail on the router, are you talking about the LNet router?
That's correct. We'll be doing that. So it's...
Yeah, so if you enable MultiRail on the LNet router, when the buffer, like when we select the buffer, the incoming message will get a buffer, and that buffer will be associated to a specific NUMA interface. And when we're sending out the message, we'll select the interface that's closest to that buffer that got allocated to receive the...
We had a situation where we were losing locks, right? So you'd recall a lock, and that would be lost, and then we'd evict a client, and those were not replayable. And so this is above this multi-rail, right? So this issue's not addressed here?
No,
okay.
That wouldn't be. Okay, thank you.